Hi, my name is Jeffrey Coldingler, and this is my Lab 2 for Physics 2211 in projectile motion. The purpose of this lab is to analyze the motion of a projectile and compare experimental data to computational models that include the effects of gravity and air resistance, or drag. The computational model uses a given code within GlowScript and inputted equations to display a comparison model to the experimental one. The experimental model was videoed throwing a ball and using the tracker to trace the position compared to the time of the projectile. The result preview: the computational model with drag better resembled the experimental model, however neither were exactly precise to the experimental. The system was the red ball and the surroundings was everything else other than the red ball. The main physics ideas are the position update formula, which is final position equals initial position plus velocity average times delta t, and then the velocity update formula, which is final velocity equals initial velocity plus F net over mass times delta t, and both of these are derived from Newton's second law. The force of gravity is also big in this. Force of gravity equals 0, negative mg, 0, and that'll always point in the negative y hat direction as it is gravity on the ball, or the force on the ball. The drag force formula is also big in this. The drag force equals negative b, which is the drag coefficient, times v squared times v hat. This is my experimental model. The photo shows the parabolic trajectory of the red ball I used for the experimental model. Using the tracker program, I traced the ball through its flight, which provided the two distance by time graphs shown in the middle. The results of the thrown ball are shown above. With the first two inputs, we can create the initial values. Initial velocity is given by the formula. Initial velocity equals R2, position 2 minus position 1 over delta t. After plugging in the first two positions and times, we end with an initial velocity of 3.099, 0.970, 0. The initial position consists of the first values, which is 3.726 times 10 to the negative third, 2.332, 0. In the graphs in the middle, you can also see the distance is linear, and this is because drag's not really affecting it. And then the y distance compared to time is kind of like a parabolic drop. For our computational model, we first insert the initial values we calculated from the last slide. The mass was calculated using a scale, which was 0.04 kilograms. We then inputted 9.8 meters per second squared for the magnitude of the acceleration due to gravity near Earth's surface. Delta t was 0.003 seconds, which matched to the speed of our tracker program. For the drag calculation, the calculations would not work with a coefficient over 0 for some reason. However, 0.002 seemed to resemble the experimental model the best. On the second part of the code, we inputted 0, negative mg, 0 for the gravitational force, and then the drag force formula was inserted. F net will be the sum of the gravitational force plus the drag force. We additionally inputted the velocity update formula and the position update formula. The computational model without drag, the code is identical to the code before, however the drag coefficient is 0, which leads to the gravitational force as the only force acting upon the ball. All initial values stay the same too. As you can see in the graphs, both computational models resemble the experimental one pretty good. The experimental one is less consistent on the y value. However, the model with the drag compares slightly better than the one without the drag. This can be directly seen with the graph comparison. All models favor each other nicely. The experimental model starts slightly above both computational models. However, in the end, the drag model closely compares to the experimental better than the one without drag. Sources of error can include the video recording error or tracker markings. The blur on the ball within the video made the tracking the center of the ball more difficult, and this could have produced a slightly off-target model. The initial velocity error could also have affected it. As stated in the ED discussion, initial velocities were causing issues with the models, and some people were having to use like the third and second time instead of the first and second. An incorrect drag coefficient could also have been a source of error. Inputting an incorrect drag coefficient, or one that varied further from the experimental model, could have caused the data to differ. For the what does it mean, do any of your models predict a terminal velocity? No, neither of my models predict the terminal velocity, as the vertical velocity is decreasing rather than becoming constant. An experiment to find the terminal velocity could be dropping tiny parachutes or coffee filters to find a precise constant falling speed. Imagine if the objects were initially thrown straight up with the same initial speed, would the time it takes for the object to reach the ground be longer or shorter? This time would be longer, as the object would have to reach the max height and fall a greater distance back to the floor compared to the original model. The vertical motion would have a longer time period to stay in the air, as there is not a horizontal component to shorten the time.